one of the classic problems involving the procedure that we're using for forces is what to do when an object is on an inclined plane. And just a couple of days ago, the reason I was gone on Tuesday was I was in San Francisco, and in San Francisco, it's insane to park a car. And when you do park a car, chances are you're on like a 60-degree incline, and you better park your car in the right way or you're going to kill somebody, and worse, you might ruin your car. So imagine here's a typical street in San Francisco. So here's the horizontal, but here's our incline, and we're going to put a little toy car on this incline. Now, you know that if you release this little car, you put it on this incline and you release it, you know it's going to accelerate down the incline in this direction. But you also know intuitively that if the incline was, just like this, a very shallow incline, if I put my car down here, it's hardly going to accelerate at all. Well, if it's flat, it won't accelerate it. And the steeper your incline, the greater your angle, we call this the angle of incline, theta, the faster it's going to accelerate until your angle of incline reaches 90 degrees. Well, what if your angle of incline was 90 degrees? I mean, what if I just took this car, and released it from an angle of incline of 90 degrees? Well, it's going to accelerate at 9.8 meters per second squared. So somewhere there's a relationship here with gravity. If the angle of incline is 0, that is, your little car is sitting right here, you get no acceleration. You incline it up, you get some acceleration. You incline it to 90 degrees, you get 9.8, your maximum. So we want to know, what's the relationship between my acceleration and this angle of incline? And we can use the procedure that we've been talking about to do that. So let's imagine we're at some angle of incline like this, and I'm going to draw the free body diagram of this guy. When you draw the free body diagram, you just draw the object. You don't draw, but you can cheat a little bit. Okay, you can cheat. Here's the incline, but we don't want to draw the incline. We just want to draw, on a free body diagram, the object of interest. Now, let's draw the forces acting on the object. Gravity is pulling us down towards the center of the earth, always towards the center of the earth. Gravity does not pull sideways. Okay. And now, here's a thought. This incline on this guy up here, we're going to say these wheels prevent the incline from applying any force that's parallel to the incline to the car. So the incline can only apply a force to the car that is perpendicular to the car. I mean perpendicular to the incline. Perpendicular to the incline. So this is the direction of the normal force. The normal force is perpendicular to the incline. Now, of course, the normal force is applied to the wheels, but I'm just going to draw it as one force going up like that. And it's perpendicular to this incline. And those, if I release the car, those are the only forces acting on the car. We're going to ignore air resistance and friction. Are these two forces? So I can now, and by the way, this is step 2 of the procedure, is to draw the free body diagram. Now, we know that this guy's going to accelerate down the incline like this. Here is a big hint, a strategy, a tactic when using the procedure. If you know, are you listening? I see somebody looking down. not intently at me like that. Okay. If you know the direction of the acceleration vector, make that one of your axes. Axes. Either your x or your y. Why should you do that? Because it will make solving the problem a lot easier, a lot simpler, a lot faster. Who wants to do physics homework all night? So I'm going to do this. See, normally we say, oh, x, we'll make x in this direction and y in this direction. If you do that, this problem is going to be crazy hard. It's possible, you can do it, but it's going to be crazy hard. Instead, what I'm going to do is I'm going to take my xy axis and I'm going to rotate it to match the inclined plane. Why do I do that? And to make the problem easier to solve. And by the way, this works for problems that aren't inclined plane problems. If you have a problem where, like, there's a centripetal acceleration that's in some weird direction, make your axis in the direction of the centripetal acceleration, and the problem will be easier to solve. All right, so now what I've got to do is I've got to finish step 3. Step 3 of the procedure was to develop your XY axis system, but the next part was to break all the forces up into their x and y components. Well, the normal force is now in the y direction. It has no x component. But now gravity, because I've tilted this, gravity is now needs to be broken up into components. And we're going to have a component that is in the y direction and a component that is in the x direction. So here's the component of gravity. It's in the negative y direction. Here's the component of gravity that is actually in the negative x direction, the way I've drawn this. Okay? Now I want to relate this to my angle of incline, and here's what I want you to believe. When I was here, when the car was down here and the angle of incline was 0, we had gravity and we had the normal direction. And you see that gravity was in the normal direction, just down instead of up. But when I take that, when I take this and I rotate it, watch what happens to the normal component of gravity. Here, all the gravity is normal. But watch what happens. I'm going to rotate up by theta. How much did the pencil get rotated from the vertical? Look at the pencil. The pencil is straight down. Then I rotate like this with my angle of incline. And now my pencil has rotated by the same angle. So look at this. If I rotate up by an angle of theta, this normal component of gravity gets rotated up by that same angle, theta. Let me zoom back down. So here's what I want you to believe. If you rotate this up by theta, theta on this little triangle is right here. Okay? If you can believe that, then we're good. Because look, now I've got an adjacent leg here. mg, now the weight is the hypotenuse of this right triangle. And the adjacent leg is the hypotenuse times the cosine of the angle. And this is the opposite leg, so it's the hypotenuse times the sine of the angle. Now this is confusing to students, because now I've got the y component of gravity is mg times the cosine of the angle. Wait a minute, I thought cosine was just for the x direction. No, not in this case. This angle is rotated from the vertical, not the horizontal. So the cosine and the sine kind of get switched. Just look at the triangle. Let the right triangle tell you what to do. The right triangle says, hey, here's my angle. So this is the adjacent leg, mg cosine theta. So now I'm done with step 3 of the procedure. I got my xy axis, I broke my forces into their x and y components, and I identified what those components were. Now I go to step 4. Let's sum the forces and, let's do the y direction first. And why? Because we don't really need to do the y direction in this problem, but you will later. It's going to be equal to 0. When I add up all the forces in the y direction, it's going to be equal to 0. Why is that? Look at this car. Is this car going to accelerate in this direction right here? I hope not. That means it's either sinking into the ground or it's being launched into the air. And that's not going to happen. You know it's going to accelerate down this way. So there's no acceleration in my y direction. So that means that the normal force, N, minus mg cosine theta equals 0, which means that my normal force is equal to mg cosine theta. And here's what this means. The normal force is supporting part of the weight of the object, but not all of the weight. Think about when the angle of incline is 0, the incline is supporting all of the weight, isn't it? I mean, when the car is down here, here's your weight, here's your normal force, they're just equal to each other. The normal force is equal to the weight of the car. But when I rotate this up, now it's not supporting all the weight. I mean, think about when it's supported all the way up, 90 degrees. Think of the car when it's right here. It's not supporting any of the weight at all. It's just going to fall straight down. Is this making sense? Okay. So, this tells you, this is how much of the weight the normal force is supporting on an inclined plane. Okay, in this situation anyway. Now, if I sum the forces in the x direction, I am going to get ma. I am going to have some acceleration now. And so what are the forces in the x direction? Well, I look at my free body diagram. The normal force has no force in the x direction, no component in the x direction. My gravity does. It's mg sine theta, and that's the only force that's in the x direction. I'll put negative in there. Equals ma. Oh, sorry. So if I sum the forces, I get negative mg sine theta equals ma. And so, look, the mass cancels out. Isn't that nice? The mass cancels out. That means it doesn't matter how big or small this little car is, it's going to accelerate down the incline with the same acceleration. So the acceleration of the car is going to be equal to, let's just talk about the magnitude of the acceleration. G sine theta. The direction is going to be down the incline. Now, I made down the incline negative x in this case, but here's the point. When you're on a hill, let's say on a bicycle or something, this is the rate at which you accelerate down the hill. A fraction of the acceleration of gravity. Doesn't that make sense? Now, if you're on a hill with 0 incline, that means you're on a plane, on a flat plane, what's the sine of 0 degrees? 0. You have no acceleration. But let's say you jump off a cliff. What's your angle of incline there? 90 degrees. What's the sine of 90 degrees? 1. So 1 times g, you're going to accelerate with g. What if you're right in between? Like 45 degrees. What's your acceleration going to be? 9.8 times the sine of 45. What is that, 0.707? So roughly 70%. So about 7 meters per second squared. And then, so what angle would you have to be at in order to accelerate down the incline at half the acceleration of gravity? That would be 30 degrees. So 30-degree angle, you'll accelerate it with half the acceleration of gravity. Kind of cool. By the way, this is how they practiced for moonwalking. They made an incline, and they suspended the astronauts from cables, so that they were, here's an astronaut, not a very, but he's in like big astronaut clothes, also known as a spacesuit, I guess. So, and they suspended him from cables, so that this, so that this component of the weight was equal to the weight that they'll experience on the moon. So they would hop around on these inclines. That was pretty interesting. But anyway, that's how you deal with an inclined plane problem. So the force of gravity is going to be down the incline, and it's going to have a magnitude of mg sine theta. That is all.